For the first scenario, where we measured it from having an initial position of 30 and an initial momentum of 0, we found that the A coefficient was equal to the initial x position. The beta coefficient was equal to the dampening coefficient divided by 2 all over the mass of the block. The omega was equal to the square root of the spring constant times 1.035 all divided by the mass of the block, and the phi value remains 0. Now, when we run the simulation, we see that both the analytical model and the model that we are given overlap each other. And we will see that for these kinds of models, if we were to reduce the dampening coefficient, the time it would take to get to each peak of these curves would shorten. Now, for the second scenario, we measure the conditions where the x position was 0 and the initial p value was 100 kilograms times centimeters per second. And analytically, we found that the A coefficient was equal to the x initial position plus the initial momentum divided by 20 over 9. And we found the beta coefficient to be equal to the dampening coefficient divided by the mass of the block. We found the omega coefficient to be equal to the square root of the spring coefficient times 1.035 all divided by the mass of the block. And in this scenario, the phi value is 29.8. And again, if we run this scenario, we see that both the analytical model and the model generated by these conditions overlap each other. And if we were to change the initial momentum of this model, both models still will overlap each other.